title that it does, if nature was quite that simple. If we go back to the 1920s, a very famous English physicist, theoretical physicist called Paul Dirac, he lived in the time when there had been a great revolution in physics. Einstein had invented special relativity. And in parallel with that, a lot of other clever gentlemen, for example, Niels Bohr being one of them, had invented quantum mechanics, and these became cornerstones of our models of fundamental physics. The problem was that Niels Bohr's model of the atom and the electrons was what we call a semi-classical model. It wasn't really consistent with Einstein's theory of special relativity. And Dirac set out to try to come up with a theory to describe the electron which was consistent with Einstein's theory. So he developed some equations that had the right properties that were consistent with what Einstein was talking about. And he solved those equations in order to try to describe the electron, and he came up with a very startling observation. He solved his equations, and there were twice as many solutions as he expected. He did indeed manage to describe the electrons, but he also seemed to be describing some new, totally unforeseen particles, which we now call positrons, or anti-electrons. Dirac came up with the idea of antimatter. Particles which behave very much like the electrons that compose us, but have, for example, opposite electric charge. He got very worried about this because we didn't see them in nature. So he managed to come up with some sort of a way of explaining it, but it wasn't completely satisfactory. Dirac needn't have worried, because all this time experimentalists were working away, and it did not take very long. This is 1928. By 1933, people had seen these mysterious particles, the anti-electrons. They turned up, in fact, in the devices those days that people used for experiments were called cloud chambers, and they were a way of visualising where particles went, where charged particles went. And Carl Anderson managed to catch positrons in his device, which were raining down, were being produced in cosmic rays, bombarding the upper atmosphere. I'll say a little bit more about cosmic rays in a little while, because they'll come into our story again. He stuck his device in a magnetic field so that a charged particle would go in a curve. And from studying the curvature, he was able to actually show that indeed these things were like electrons, but they were bending the wrong way. So we had seen the first evidence for antimatter, which Dirac seemed to need to understand his new equations. Antimatter, one thing I would like to get across to you is that antimatter is really as real as matter. Okay? This is a more recent picture of what's called a bubble chamber. It was like the successor to the cloud chamber, and there's these beautiful artistic pictures show where charged particles go when there's an interaction of a particle in one of these bubble chambers. Absolutely beautiful devices. And what you can see up here is what's happened here is that this particle coming along here, curving in a magnetic field, has emitted another particle. It's a photon, right? A particle of light, if you like, but a much higher energy, which has travelled across here, and then, whilst it's going past another atom, basically it has disappeared and turned into an electron and a positron pair, which have opposite charge and they curve in an opposite direction in the magnetic field. If you can't see that picture very clearly, here's just that bit, which has been drawn over here. This red guy is an electron curling up and losing energy in the magnetic field in which it's found itself. This one is a positron. This yellow guy here is the photon, which has disappeared. This is like Einstein's idea in reverse. We're using the energy being carried by that yellow photon to create the mass of these two matter particles. So E equals mc squared. is being used. And to me, that antiparticle looks as real as that particle, at least to my eyes. Okay, so they're not something very mysterious. It's just that there's not many of them about. You have to do clever things to make them. Many of you will be familiar with PET scanners. In fact, antimatter is so common nowadays that we can use it in medical research or in medical diagnosis. This is an example of a PET scanner at Westmead Hospital, where the patient is placed in there and the patient is injected with a small amount of a radioactive isotope which decays. It moves around the body and it decays at a certain place in the body, wherever it's got to, and we see what it decayed into in the following way. Here's a part of the body. Here's my radioactive, usually it's a fluorine-18 atom, I think. It decays and it spits out a positron. It spits out an antimatter particle called a positron and a neutrino. The poor old positron doesn't go very far. It might go a couple of millimetres or something like that, at most, until it finds an electron, of which there are many in our body, and it annihilates, destroys itself and the electron to give out two particles called the photons, and we detect those photons using devices sitting around here like that. And by seeing where the photons come from and getting lots of them, we can figure out where our antimatter positron was, and we can reconstruct an image of that part of the body, as for example being an image of the brain. So one can see brain activity and follow brain activity using antimatter. Okay? The E plus and E minus annihilate just in the same way as Paul and I would have annihilated if he is indeed made of antimatter. Okay, so I want to get across that antimatter is not particularly mysterious. Let's come back to this idea of symmetry. And let's ask ourselves, are the laws of physics, our basic laws that we use to try to understand nature, are they symmetric under all circumstances? Which sort of is aesthetically pleasing that they might be. I'm going to tell you about a particular two types of symmetry which feature in our story tonight. The first one's got a fancy name. It's called parity, and we give it the symbol P. What it really means is reflection in a mirror. We ask ourselves the question, if I hold up my left hand to a mirror, what do I see in the mirror? I see a right hand. Okay? And we ask ourselves, would I expect to see something such as that right hand in our real world? And if I would expect to see it, and I think for a right hand I would expect to find right-handed people, one would conclude that people would appear to be, the operation of looking in a mirror would produce a system which we would equally expect to be able to find in nature. If that was not the case, nature would not be symmetric under this operation of examining any sort of physical system in a mirror. Okay? Would we expect to see this, or would we expect to see this? So that's a rather fundamental question. It turns out for a very, very long time people believed, well, of course, we would expect to be able to see the things that we see in the mirror. Nature would use those as well in our everyday world. It's called parity. Once we've got the idea of antiparticles, and we've seen that they are real objects, just like particles, matter and antimatter, we can ask ourselves the question, what would you do if you had something that was made of matter and you turned all of the particles in that matter into antiparticles? Would nature use